When we balance oxidation-reduction reactions, we have to conserve mass and conserve charge. A half reaction is either the oxidation by itself or the reduction by itself. For example, when iron rusts, there are many steps in this process, but two of them are this one here and that one right there. And you can see that the one on top is a reaction in which we are losing electrons, and loss of electrons is oxidation. And the bottom reaction is a reduction. We're gaining electrons. These are examples of half reactions. The overall reaction would be the sum of the half reactions. Let's write half reactions for this equation here. We're going to start with iron 3 on one side and iron 2 on the other side. Clearly, that's going to be the reduction because we're going to be gaining electrons. The other half reaction is going to involve the oxidation of the tin 2 ion. And what we need to do is include the electrons in these half reactions. We're going to need 2 electrons that are going to be released or given off whenever we oxidize tin 2. Whenever we reduce iron 3, we also need 2 electrons because we need to make sure that those electrons cancel. In other words, however many electrons are lost, that must equal the number of electrons that are gained. So you can see that we have 2 and 2 here, and if we were to add these two half reactions, we would get the overall equation. But whenever we write the half reaction, we have to include the electrons. Later on, in a very short time, we're going to be talking about an electrochemical setup. And typically when we talk about an electrochemical setup, one half cell contains the before and after varieties of the oxidized substance, and the other half cell contains the before and after varieties of the reduced substance. So if we were to actually set up this reaction somehow, the oxidation reaction would be taking place in the oxidation half cell, and the reduction of iron 3 would be taking place in the other half cell. Of course, we would need to connect these somehow, and we'll talk about that later. In line notation, the oxidation half cell is on the left, and the reduction half cell is on the right. The typical pattern includes these various species. The oxidation half cell begins on the left with the oxidized thing, and then we put a single line, and then we write what it turns into. The oxidized thing is a reactant, and what it turns into is a product. So if we are given an equation, that kind of gives us a hint as to what we need to put where. Then, between the two half cells, we put a double line, and for the reduction half cell, we first write the thing that is reduced. This is a reactant. And then we put a single line, and then we write the formula of what it turns into. So we note that there's a double line there, and there are single lines there. There are several variations on line notation, but what never changes is that the change due to the oxidation is shown on the left, and the change due to the reduction is shown on the right. Occasionally you'll see something in line notation that has more than just these 4 things, and we'll explain that as we go on. The simplest line notation for the last problem, which involved this balanced equation, would be the following. That's what's oxidized, that's what it turns into, that's the formula of the substance that is reduced, and that's what it turns into. Notice that we don't put coefficients in line notation, and while the oxidation is shown on the left and the reduction is shown on the right, line notation typically goes reactant, product, with the oxidation, as I said, taking place on the left and the reduction being shown on the right. Let's write the simplest line notation for the reaction between magnesium and hydrochloric acid. Now, hydrochloric acid is a strong acid, so if we are writing a proper equation, we would write the hydrogen ion and the chloride ion separately. If you've had any experience with this at all, you might realize that the chloride ion will be a spectator. The reactants will be magnesium and the hydrogen ion from the acid, and the products will be the magnesium ion and hydrogen gas. And then we would balance this with a 2 in front of the H+. Notice that atoms balance and charges balance. We have the same number of magnesiums on each side, 1. We have the same number of hydrogens on each side, 2. And the net charge that's shown on the left is 2+, and that equals the net charge that's shown on the right. When we write line notation in the simplest form, we write the thing that is oxidized and then what it turns into. Well, what's oxidized here? Oxidation is loss of electrons. So who loses electrons? I think it's the magnesium. And what it turns into is the magnesium ion. Then, what is reduced? And reduction is gain of electrons. So hopefully you can see here that the oxidation number of the hydrogen goes from 1+ on the reactant side to 0 on the product side. We're going to write H+ and H2, and that shows the reduction. Whenever we do an electrochemical setup, whenever there's an electrochemical reaction, we need a solid on which these reactions occur, these half reactions occur. And if you look in this equation here, you can see that on the right side there's no solid there. The H+ is aqueous and the H2 is a gas. So there is something extra in here that is required in order for this reaction to take place. Sometimes the electrode can be one of the reactants, and magnesium, solid magnesium, that would work perfectly well as an electrode because it's a solid surface on which the oxidation of magnesium could take place. We would need something extra with the hydrogen. Probably what would happen on this side, and we haven't talked about this yet, but the hydrogen would be reduced on a platinum electrode, which is an inert electrode. It doesn't actually take place in the reaction, it just provides a surface for, in this case, the reduction of hydrogen ion. If we look at the equation near the top of the screen that's in blue, we can see that there are no solids shown there either. So we would need an electrode on both sides. The one that occurs with the oxidation is called the anode, and the one that occurs with the reduction is called the cathode. And the way I remember that is oxidation down here in the lower left starts with a vowel, and anode a little bit higher on the left starts with a vowel. On the bottom of the screen, reduction starts with a consonant, cathode starts with a consonant. That's how I remember that oxidation always occurs on the anode and reduction always occurs on the cathode. But that's a story for another day.